of arc trigonometric functions. So we were on exercise 1.2.1. We did up to number 13, so we can finish off the rest. So I hope you did some of them and you got some practice, so you get the hang of how to work out these questions. Because like I always say, the key is to practice. So let's look at the next one, which is number 15. For 15, we have y is equal to sec inverse of 2x to the power of 1 over x, and we want to work out its derivative. So here, the easiest thing to do might be to take logarithms on both sides. There's usually more than one way to do it, but in the end, we always get to the same answer. So if we take logarithms on both sides, we have 1 over x sec inverse of 2x. And then working out this derivative is simpler than working out the derivative of that one. So the derivative of ln of y, this is y prime over y. And on the right hand side, we need to use the product rule over here. So the first one as it is, you have 1 over x, and then you multiply by the derivative of sec inverse of 2x. So remember, the derivative of sec inverse of 2x, in our numerator, we have the derivative of 2x, which is 2. And then in the denominator, we have our f of x, which is 2x. And then the square root of our f. Yeah.
You forgot the ln. 1 over x times ln. You didn't put ln.
Oh, here, yes. Let's see, this is ln of 2x. So first we have 1 over sec inverse of 2x, and then we multiply by the derivative of sec inverse of 2x. So we said the derivative of 2x in the numerator, and then we multiply in the denominator our f of x, which is 2x, and then the square root of our f of x squared. So that will be 4x squared minus 1. Okay, so that's the first part of this derivative. Okay, then the second part was still not done because we no, that is the first part. Then the second part is the derivative of 1 over x. And then we multiply that by ln of this. So the derivative of 1 over x is minus 1 over x squared, and then multiply that by ln of sec inverse of 2x. Okay, so just check that everything is fine. Say that this one as it is, the derivative of ln is 1 over this, then times the derivative of sec inverse, which is that's fine, and then the derivative of 1 over x is this, and multiply by the second one as it is. So we want y prime to be the subject, so we multiply by y throughout, so we have y prime. This is y, multiplied by, so here you can see that the 2's will cancel. So we have 1 over x squared.
Yeah,
So
so
x times x So that x times that x will give us x squared, and then we have sec inverse of 2x times this square root. So sec inverse of 2x square root of 4x squared minus 1. And then we subtract ln of sec inverse of 2x. Then this is divided by 2, by x squared rather. Okay, and then this y, you can always rewrite it like that. It's not very long, not very complicated. Combining these two fractions, I think, is more than you need to do. So just replacing the y would be sufficient. In number 17, we have y is equal to ln of e to the power of minus x cosec inverse of x over the square root of 1 minus x. Okay, so here, before we even get into differentiating it, it would be easier to use our laws of logarithms to simplify this and then differentiate. So we can say that y is equal to, we'll have ln of e to the power of minus x. So I have ln e to the power of minus x plus ln of cosec inverse of x and minus ln of the square root of 1 minus x. So this one, we can still simplify it to minus x, and this one will be half times ln of 1 minus x. So our y is actually equal to minus x plus ln of cosec inverse of x minus a half ln of 1 minus x. Okay, so this is much easier to differentiate than the first one. Well, the original way it was stated, because there we would have to use the product and the quotient rule, which can be quite tedious. So if it's possible to simplify your work before you start, I would advise it. Ashikoto. Okay, so now we differentiate y prime. This is minus 1. And then the derivative of ln of sec inverse of x. So it's 1 over, yeah.
Can you quickly help me to go back to the previous page? Oh yeah, okay.
Okay, so the derivative of ln of this is 1 over whatever you're taking ln of. So we have 1 over cosec inverse of x, and then we multiply by the derivative of cosec inverse. So remember our arc trig functions that begin with c, their derivatives are negative. So this is negative 1 over x, the square root of x squared minus 1. So this is exactly the same as the derivative of sec inverse, except it's negative. And then the derivative of this one, we have negative a half times 1 over 1 minus x, and then we multiply by the derivative of 1 minus x, which is minus 1. Okay, so I want to simplify this as far as possible. So we have y prime. This is minus 1 minus 1 over x cosec inverse of x square root of x squared minus 1. And here we have negative and negative. That will become positive. So we have 1 over 2, 1 minus x. So you can rewrite this so that the positive term comes first. That is usually what we prefer. It looks nicer that way instead of starting with a negative, negative, and then the positive. So what I mean is you write it as 1 over 2 minus 2x minus 1 over x cosec inverse of x square root x squared minus 1 minus 1. But there's no difference between this and that. It's just this one looks better when you start with a positive number instead of a negative number. And then we have number 19. Number 19, we have tan inverse of xy is equal to e to the power of x plus x e to the power of y. So here you need to remember that y is a function of x. So when you're differentiating xy, you must use the product rule. Same thing over here. When you're differentiating this, you must use the product rule and include your y prime when you are differentiating the y. So the derivative of tan inverse, we know, is in the numerator. We have the derivative of the function. So the derivative of xy is x y prime plus y. So use the product rule to differentiate this. The first one is the derivative of y is y prime, then the derivative of x times y, that's what you get. So that's our numerator. And then in the denominator, you have 1 plus the function squared. So that's x squared, y squared. That is the derivative of tan inverse. Then on the right hand side, we have the derivative of e to the power of x. It's just e to the power of x. And then this one, we must use the product rule again. First one, x as it is. Then the derivative of e to the power of y is e to the power of y times the derivative of y, which is y prime. And then we have e to the power of y. So that's the derivative of x, which is 1. And then we multiply it by the second function as it is. Okay, from there we want y prime to be the subject. So we collect all the terms with y prime on one side, everything else on the other side. So I'll have y prime x over 1 plus x squared y squared minus x e to the power of y, and this is equal to e to the power of x plus e to the power of y minus y over 1 plus x squared y squared. Okay, so all the terms with y prime on one side, x over 1 plus x squared y squared minus x e to the power of y, then the terms without y prime, e to the power of x, e to the power of y. Yeah, go ahead.
Could you go back one step?
Which step?
where you before you factorized out y prime.
Yeah.
How did you manage to get okay, I see. It just I didn't see that step.
Okay. Right. Okay, and then from there, I don't want to write it in a very complicated way, but we want y prime to be alone. So we divide by the bracket on both sides. So you can work on it a little bit to make it look nicer, but essentially what you have is this. Okay, so you could combine these two to make a single fraction. Same thing over here to make a single fraction, and then simplify that further to make just one fraction instead of dividing one fraction over another. So you can work on that, but that is the answer that you should get. So you can see that with these arctrig functions, there isn't really too much to do with them. Just like with our table of standard derivatives, if you know what the derivative is supposed to be, all you need to do is substitute in the right place and then you will get the derivative. Okay, so that is it on the arctrigs. Like I said, all the other questions that I didn't do in the exercise, go and practice them. It is always good to practice. That is how you assure that you have actually learned the section. Then our next section is what we call the hyperbolic functions. Okay, so these hyperbolic functions, they look like trigonometric functions, and when we're working with them, you will see some relation, but we refer to them as hyperbolic functions. So they are functions that include e to the power of x and e to the power of minus x. The first one we have is the hyperbolic cos of h. So you can see it's cos, but this h over here, you say this is the hyperbolic cos or cosine of x. So that's how we call it, the hyperbolic cosine of x. Now, what does hyperbolic cosine of x mean? This one, very simple. This is just e to the power of x plus e to the power of minus x divided by 2. So a short way of writing this fraction, e to the power of x plus e to the power of minus x divided by 2 is, we call this the hyperbolic cosine of x. Then we have the hyperbolic sine of x. Hyperbolic sine of x. This is e to the power of x minus e to the power of minus x divided by 2. So you can see these are similar. The only difference is with cos we have plus, with sine we have minus. Okay, so this is the hyperbolic cosine, hyperbolic sine of x. And the tan is obviously defined in the same way. We say sine divided by cos. So the hyperbolic tan of x, this is e to the power of x minus e to the power of minus x over e to the power of x plus e to the power of minus x. So if you take this function divided by that one, you can see this divided by that, the division will change to multiplication. Sorry, this one, sine divided by cos. The division will change to multiplication, and then you have the reciprocal of your hyperbolic cos, and then the 2's will cancel, and then this will be in the denominator like we have over here. So this is just equal to hyperbolic sine over hyperbolic cos of x. And then we have the hyperbolic secant, hyperbolic cosecant, hyperbolic cotangent, like we do with the trigonometric functions. So our sec hyperbolic, this is, remember when we're talking about trigonometric functions, sec was the reciprocal of cos. So the same thing is true over here. Just take the reciprocal of this. So hyperbolic sec is 2 divided by our numerator over here. So this is 2 divided by e to the power of x plus e to the power of minus x. So this is 1 over the hyperbolic cos. Same thing with the hyperbolic secant. This is the reciprocal of the hyperbolic cos, hyperbolic sine, sorry. So this is 2 over e to the power of x, e to the power of minus x. Zakaria, what's happening? Thank you. Okay, and then same thing with the hyperbolic cot. This is 1 over hyperbolic tan, and this is e to the power of x plus e to the power of minus x divided by e to the power of x minus e to the power of minus x. And this, of course, is the same as that. Okay, so keep in mind everything we learned under trigonometry, we will use them. So there will be some similarities between the two. So even here we do have some identities. The first one, look at some identities. The first one is okay, so we want to work out what is hyperbolic cos squared minus hyperbolic sine squared of x equal to. So we know what each of these are, so we can write them in fraction form and then work it out. So this is just e to the power of x plus e to the power of minus x divided by 2 squared. That's our hyperbolic cos. And then e to the power of x minus e to the power of minus x divided by 2 squared. That's hyperbolic sine. So when we square this, you know how to square it. This is e to the power of 2x plus 2 e to the power of 0, actually, because you say e to the power of x times e to the power of minus x. The bases are the same, so you add the exponents. You say x plus minus x, you get 0. And then you have e to the power of minus 2x divided by 4. Then the same thing over here, you have e to the power of 2x minus 2 e to the power of x plus minus x, which is 0, and then e to the power of minus 2x divided by 4. So our denominators are the same, so we can add the two fractions together. So e to the power of 2x minus e to the power of 2x, that will be 0. So these two will cancel each other out because one is positive, the other one is negative. And then e to the power of minus 2x minus e to the power of minus 2x. So one is positive, the other one is negative. They will cancel each other out. And then here, 2 times e to the power of 0. This is just 2 because e to the power of 0 is 1. So I have 2 minus negative 2. That's 4. So I have 4 over 4, and my answer is equal to 1. So our first identity is that the hyperbolic cos squared minus the hyperbolic sine squared is equal to 1. And you can relate this one to cos squared x plus sine squared x is equal to 1, if you remember that. So different because the sign over here you have positive, here you have positive, and over there it is negative, but they are both equal to 1. So with the hyperbolic, between them you have a negative, with the trigonometric you have positive. So that is something for you to look out for. When the trigonometric was positive, maybe in the hyperbolic we will have positive, or it'll be the opposite sign. I can't remember what I said. Okay, so we can look at more trigonometric identities. Let's look at another one. This time, what if we try to add them? Let's say we have squared plus is squared. We do the same thing. This time,
Miss,
yeah.
Is this problem number 2?
Yes, this is the second identity.
Okay.
Okay, so we want to see what this is equal to. So cos, hyperbolic cos, we said e to the power of x, e to the power of minus x divided by 2. Then we must square it. And then e to the power of x, e to the power of minus x divided by 2. And then we want to square that. So squaring it the same way we did the other one, we have e to the power of 2x plus 2 e to the power of 0, then plus e to the power of minus 2x divided by 4. And the second one, we have e to the power of 2x minus 2 e to the power of 0 plus e to the power of minus 2x divided by 4. So again, you can see our denominators are the same, so we can just add the numerators of the two functions. So I have e to the power of 2x plus e to the power of 2x. This gives me 2 e to the power of 2x. I have e to the power of 0 plus negative e to the power of 0. That will give me 0, because this is 2 plus negative 2 is 0. And then e to the power of minus 2x plus e to the power of minus 2x. That is 2 e to the power of minus 2x. And then my denominator is 4. So we can see that 2 is a common factor in the numerator. So we can take it out. So we have 2 e to the power of 2x plus e to the power of minus 2x divided by 4. And this is e to the power of 2x plus e to the power of minus 2x divided by 4. And this looks very similar to the cos hyperbolic of x, and this is in fact equal to the hyperbolic cos of 2x. So this time instead of x, because you can see our exponents are not just x and minus x, our exponents are 2x, excuse me, and minus 2x. This is not 4, this is 2. I think that's what somebody wanted to tell me. Okay, so this is like hyperbolic cos of x. So with hyperbolic cos, you have x and minus x. This time I have 2x and minus 2x. So this is the hyperbolic cos of 2x. Okay, so this one, again, your mind should be thinking back to the trigonometric functions. If you remember, we had this one here where we had cos squared x minus sine squared x. This was equal to cos 2x. And now with our identity, we have a plus instead of a minus. So you can see the signs are switched, but the idea is the same. And it is equal to cos 2x. So I just want to shift this so I can write the identity all together. Okay, so the identity, just write it in a different color to distinguish it, is this squared. Okay, so this is our second identity, that this hyperbolic cos squared plus hyperbolic sine squared is equal to cos hyperbolic of 2x, which you can relate to this one that we did when we're looking at trigonometry. So the only difference again is with the hyperbolic, the sign changes from negative to positive, like with the first one that we did. So with the first one, from trigonometry, it was cos squared plus sine squared is equal to 1. Then with hyperbolic, the plus changed to minus. And the same thing happens over here with the hyperbolic, the minus changes to a plus. So those are some of the ways you can use to remember what it is we are doing. So another trigonometric identity, so number 3, is that 1 minus the hyperbolic tan of x. This is equal to the hyperbolic of x. So this one you can work it out for yourself. So keep in mind that this comes from the first one. So this is how you would do it.
Miss,
Yeah.
Can we be asked also like to prove the identity
Yes,
is in
you
the
can.
hyperbolic?
You can be asked to do that. Yes. Okay, so this one comes, oh, sorry, this one in black, I get it from that one. So just like with trigonometry, we would divide by cos on both sides. So here you can see if I divide by the hyperbolic cos, I get 1. And then sine hyperbolic divided by cos hyperbolic is tan. And then 1 over sine hyperbolic No, I divided by cos, sorry. So 1 divided by cos hyperbolic is sec hyperbolic squared. Okay, so you can see this one, I get it from that one. So if you know this one, remembering that one, you just need to remember, okay, I need to divide everything by cos hyperbolic squared. Then the next one, number 4, we have the cot hyperbolic squared of x minus 1. This is cosec. Okay, so you can see the only difference with the trigonometric functions is that the signs are different. With trigonometric functions, here you had a plus, but with the hyperbolic functions, you have negative. Okay, so this one also comes from this identity here in red. So to get that one, all I do is I divide by the hyperbolic sign. So cos over sine is cot. Sine over sine is 1. And then 1 over sine is cosec. So you can easily show the working of how I got this from that one. That shouldn't be too difficult to do. And another one. This is okay, so this one, the hyperbolic sine of 2x, this is equal to 2 hyperbolic sine of x, hyperbolic cos of x. So you can also try and work out this one, maybe think about it. Hyperbolic sine of 2x, by definition, this is what it is equal to. And this one, I think you can use your difference of squares to write this out. So e to the power of okay, so this one, I want the 2 to be over here. So I can multiply by 2 and then also divide by 2. So if I put a 4 over here, you can see that this 2 and that one will cancel, so that I have this 2 here, because I'm trying to work out my identity. So somebody asked the question, can we be asked to prove that? So if this is what you were given, you start on the left-hand side, you use the difference of squares, and then you introduce this 2 over here. But when you put a 2 over here, you must put this 2 here, becomes a 4, so that when they cancel, I'm left with a 2 in the denominator. And then I have e to the power of x, e to the power of minus x, and then e to the power of x plus e to the power of minus x. And then from there, these 2, you can split them up. So let me do it over here. This is 2 times e to the power of x, e to the power of minus x over 2, e to the power of x plus e to the power of minus x over 2. So you can see when I multiply this one in that, I get this fraction over here. And this is sine hyperbolic. This one is cos hyperbolic. So this is 2 sine hyperbolic, cos hyperbolic, which is my right hand side. Okay, so that is how I would work that one out. And the other identities that come after this, you would do them in the same way. So if you're given something like this, if you're not sure what to do, try and rewrite it in terms of e to the power of something and then simplify as far as possible. So that's identity number 5. Then number 6, like sine of x plus or minus y. This one is pretty much the same as the one with sine of x plus y. Yeah.
Saying we are required to know where the identity comes from instead of just memorizing like we did in with the trigonometric identities.
I think with trigonometric identities, we knew where they came from. You should know how to get them. I don't know. Your question was, are you supposed to know where they came from instead of just memorizing them? Was that your question?
Yes.
You should know where they came from. And I think even with trigonometry, you should know where they come from.
But we were not required to know. We could have just memorized them and used them to prove other equations and stuff.
Like
in the technicon, there's also not questions, practice questions that ask us to show how this identity is brought about.
Yeah, they may not be there, but in the test, you may be asked. I think you've noticed Mr. TK doesn't just ask questions from Technicon. So you should know. I don't think there's anything difficult I did here with actually proving that. It's just, are you able to simplify the fraction to show that the question can come, it may not come. Knowing it doesn't hurt you. Okay, that's how I feel anyway. Okay, so this is the another identity that we need to know, and I see identities are part of the course outline, even though they are not. There are no questions in the Technicon. I see them. There is a section on identities in the course outline, so you should expect some questions, at least with the basics you should know. Anyway, so this one here, what this means is that if it's plus, then the sign over here will be plus. If it's minus, the sign over here will be minus. So this is just the same as when you had sine of x plus y. Sorry. I'm distracted a little bit. And this is okay, sorry about that. Okay, so if you remember, with the sine of x plus y, you would say sine of the first one times cos of the second one plus sine of the second one, cos of the second one, cos of the first one. So that identity is pretty much the same. When you're adding, even here you're adding. When you're subtracting, even there you are subtracting. So it is pretty much the same. And the next one.
How do we prove that using the hyperbolic?
You would have to rewrite it in terms of e to the power of something, like I did with the previous one. Like that. E to the power of x plus 1. Yeah.
We can go back to the previous page.
This previous page.
I know. Yeah, that one.
Mhm. So the easiest way to prove some of these identities is to rewrite them as exponents and then use your laws of exponents to work them out.
Please go back to the
Please mute your mic if you're not speaking anymore.
M.
Go ahead.
Would you say sine? I mean the number 6. Would you say sine h plus sine h or sine h minus sine h? How would you prove that?
How would I do what?
Could you please just demonstrate how
I
you
demonstrated the previous one. You must try this one. I think sometimes the problem is you don't even try it. You just look at the question and you are not thinking. You do actually need to try it for yourself. So try it with the previous one I showed you. Guys, please mute your mics if you're not speaking. Okay, so what you would need to do, Erasmus, your mic is still not muted. You have background noise. Thank you. Right, so the easiest thing to do is rewrite it as e to the power of x plus y minus e to the power of negative x plus y divided by 2. Then you use your laws of exponents to simplify it. So I'm sure you know how to use the laws of exponents. There are times where you have to be a little bit creative, like I did over there, where you add a 2 that wasn't there because you can see where you are going. Okay, but you do need to actually try them. Don't just look at something and think, oh, I can't do it. Most of these, when you actually start doing them, you'll be surprised you can do them. Okay, then the next one involves the hyperbolic cos. So hyperbolic cos of x plus or minus y. So here, what happens is the signs are switched. We have no, they're not. We have cos. Okay, so again, you can see it's similar to the one with cos x plus y, except here with the hyperbolic, the signs are switched. With cos, it would be minus and plus. You'd have cos squared minus sine squared, but here when it's plus here, you have a plus there. When it's minus there, you have a minus over there. Then number 8. Okay, so this one identical to the one with tan. Okay, so I'm sure this one, okay, I don't know why it's flashing. Okay, maybe my connection is about to go off. I don't know why it's flashing. Let's see. Okay, it's not flashing on my screen. Okay, it looks like it's fine now. So this one, you can easily get it from, what was it? Cos hyperbolic squared plus sine hyperbolic squared is equal to 1. That is where it should come from. That one should be easier to prove than that one. You don't even need to write them in terms of e to the power of something. Then number 10. Then this one, again, in the same way, you should be able to get it from hyperbolic cos squared plus hyperbolic sine squared is equal to hyperbolic cos of 2x. And then you play around with it, and then you should be able to do it. So all of these, again, like I said, I'm sure if you were to just sit down, think about it, you would be able to prove them. These ones involve laws of exponents, but multiplying e to the power of x, e to the power of minus x. If you use your laws of exponents, you shouldn't have any problems. Okay, so some more. So for today, we will just look at some definitions. I just want to finish off some more. That was number 10, 11, but these again are all listed in your book. So the hyperbolic sine of minus x, this is minus the hyperbolic sine of x. This is also true for sine of x. If you have sine of minus x, that is the same as negative sine of x. So we call a function like this odd. So if you put in a negative of a number and the answer is negative of what you get, if what you had put in was positive, then we say that is an odd function. Then 12, we have the minus, and this is the same. That okay? So this one is what we call an even function. So whether you put in the negative number or the positive number, the answers are the same. Then what you have is an even function. So there are some functions that, besides these ones, that are odd or even. For example, x squared. X squared is an even function because if I say 1 squared, my answer is 1. Negative 1 squared, the answer is still 1. So whether I put in a negative or positive of that number, the answer is the same. That is what we call an even function. And then x cubed is an odd function. Okay, because if I have 1 cubed, my answer is 1. And negative 1 cubed is negative 1, which is negative of 1 cubed. Okay, so yeah. Then let's just finish off the list. 10, hyperbolic 10 is an odd function. And cosec hyperbolic is odd because it's just the reciprocal of an odd function. Okay, the brackets are not necessary there. And then hyperbolic sec is even because it's the reciprocal of an even function. And then cot is odd because it is the reciprocal of an odd function. Okay, so just write that any function f of x such that f of minus x is equal to f of x is even. Excuse me. And then if f of minus x is equal to minus f of x, then the function is odd. Okay, so keep in mind that a function does not have to be even or odd, or if it's not even, does not mean it is odd. So it can be neither even nor odd. But this is just some of those mathematical definitions that you need to take note of. Okay, so since you have the book, you can just read up on what we have to do, but make sure you have done the exercises, the questions in the exercise, in the previous exercises that I did not do, because it is very important that you practice. Okay, so we'll stop here for today and we meet tomorrow at 2 o'clock.